Let's do the inert pair effect. Okay, and I'm going to be referring to, in the reader, if you own one of these things. Let me flip over there. This would be page 71. So pay attention to the closest periodic table you have to you, or the one on the screen, whichever you prefer. Say I give you something like lead. Okay, and I say this is a metal. Metal, if I tell you it's a metal, which hopefully you would know, because it's to the left of this staircase. But if I say it's a metal, that means it will only have what kind of charge? A cationic or anionic? Cationic, only positive. And so the inert pair effect basically tells you that you can either count from all the way on the left side, so that would be like 56, 50, 55, 56, 81, 82. So 4, you remove 4 electrons to get there. So this can be plus 4. Or you can start counting at 81, so thallium, 1, 2. So plus 4 and plus 2 would be common charges there. Let's say we take something like arsenic, and I tell you this is a semi-metal. If I tell you it's a semi-metal, I mean that this could have positive or negative charges. So it'd be cation or anion. Let's do the cation first, so the metal charges. You count all the way over from potassium, so 19, 20, then 31, 32, 33. That's 5 spaces over, or this could be plus 5. Or you could start counting from gallium, number 31. So 31, 32, 33, that's 3 of them. So this could be a plus 3. So the inert pair effect gives you both of these, or most specifically the second set of numbers is from the inert pair effect. Then, if you know it's a semi-metal, that means it also could have a negative charge, so you count from the other direction, so starting at krypton. So you go 1, 2, 3 over to arsenic, so this could also be minus 3. Okay? Now, what you see in the reader here is that the top side is if it's a metal. Okay, if it's a metal, you'd get those charges. If it's a non-metal, you'd get the ones on the bottom. And if it's a semi-metal, you'd get both. So these are just predictors. That doesn't mean what it actually is, but these help you predict it. The first number in the top row here, the 1, 2, 3, and 4, are the numbers from the inert pair effect. Okay? So I just want you to predict it. If you take a look on the left-hand side, this is just in reality what are common charges. So you wouldn't have to memorize these because some are less predictable. But I just wanted to show you how the inert pair effect can predict a lot of these numbers. Okay? So it's this part that you would need to know. And any metal I give you, you'd want to be able to predict the charges. Okay, if there's no questions, let's go to the next thing. Alright? Let's do a Lewis structure example for main group. Okay, so what you can do is really pick anything from that section. Let's for fun. So any acid would work, especially one with lots of oxygens. And really any chemical that we mentioned in main group might be fair game. So let's just pick an acid for fun. Let's go H2SO4. So we learned this in 2A. Let's just do a little refresher here. The way I do it, especially if it's not, we'll do a Lewis structure in organic as well. But for this, if it's not organic, I always go through the same method that you might have seen in 2A. So you count the valence electrons. There's 2 hydrogens in column 1. There's a sulfur in column 6, and then there's 4 oxygens in column 6. Let's see, that turns out to be 32. What is the center atom? Sulfur. Yeah, you see sulfur within a list of 4 oxygens around it. So that would mean the 4 oxygens are surrounding it. Where are the 2 hydrogens? On the sulfur or on the oxygens? On the oxygens. You can pick any 2 at random. Doesn't matter which 2 you pick. And what you'd want to remember is, if it's an acid, the hydrogens would be on the oxygen, not on the other element. So now you construct what I call the skeleton, which is the bare bones, just straight up bonds. Okay? And so we count the bonds. Each bond counts as 2 electrons. 2, 4, 6, 8, 10, 12 of 32. I need to fill in 32 electrons. I have 12. Now I go to terminal atoms. That's atoms on the outside. So, and I fill an octet in each of them. So I at 12. So I pick a terminal atom at random. 12, 14, 16, 18, 20, 22, 24 of 32. Now I go over to the hydrogen, but a hydrogen can't have more than 2 electrons. So the hydrogens are maxed out right now. So now I'll go to more internal atoms. I'll go to the next set of oxygens. I think I was at 24. Does that sound right? Okay, 24, 26, 28, 30, 32. So I have 32 of 32. By the way, if I had more electrons to fill in, where would I go next? To the sulfur. Is there a question? Yeah. What you're thinking about is for organic, and you could do that here, but it's a little easier to do it this way when it's not organic. When it's organic, you'll see that method you're referring to, and I'll alert everybody when we get to the organic example. Alright, so now you ask yourself, first, does everything have an octet? What do you think, yes or no? Yeah, we're pretty good with octets. So second, after you check octets, that's 8 electrons around each atom. Now you check the formal charge. So, what is the formal charge of that atom right there? 0. Yeah, it's 0. Should I review formal charge, yes or no?
Yes.
Yes? Okay. So, this is my method. If you learn it in another class, it will probably be a different method. You go over to the column number, and I'm talking about the Roman numerals that you see in the periodic table next to the letter A. Oxygen's in column 6A, or column 6. So when you go over here, I count the number of items or things around it. And so I go 1, a bond, 1, 2, 3, another bond, 4, 5, 6. So it's in column 6, it has 6 items around it, it's a formal charge of 0. Same with this one right here. This is also 0 for the same reason. If you do hydrogen, it's in column 1 or 1A, and it has 1 thing around it. So if it's a match, it's 0. Now let's try another one. Take this oxygen here. Oxygen again is in column 6, but this has 7 things around it. 6 electrons and then 1 bond. So a total of 7. Let's double count. 1, 2, 3, 4, 5, 6, 7. It has 1 over what it's supposed to have, or 1 too many electrons. So this is a -1 overall formal charge. The same would be true with the one at the top. Take a look at sulfur now. Sulfur is in column 6 as well, but if you count the number of things around it, it'd be 4. 4 different bonds. So it's 4. It's under the number of electrons by 2. It should be 6. It's under by 2. So this is a +2. Alright, what's the ideal formal charge? 0. +1 and -1 are okay. Anything out of that range is terrible. So this is not a good structure. In order to fix the structure, what you want to usually do is make multiple bonds, or double and triple bonds. So you usually fix it around the area where the formal charges don't look good. So what I would do is take the oxygen on the top and bottom right now. Let me redraw it. Okay, I redrew it. And now what I'm going to do is take 2 of the electrons, any of these 6, any pair, cancel them out 2 at random, and make it a double bond now. Okay, now we take a look at it. What's the formal charge of the oxygen on the top? It would be 0. It's in column 6 and there's 6 things around it. Formal charge of this one down here? In column 6, there's 7 things around it. It's over by 1. It's a -1. How about the sulfur? +1. Notice that the sum of the formal charges will always equal the overall charge on the molecule. So -1 + 2 - 1 will equal 0. Or in this case, +1 - 1, +1 - 1 equals 0. So that's cool, but not the most ideal. We prefer zeros everywhere. So do the same thing again. Pick a pair at random, scratch it out or erase it, and then make another double bond. And in this case, all the formal charges will be 0 now. There's just one issue. We broke the octet on the middle sulfur. Is that okay? It is okay because it's an exception. Anything below the row with carbon in it, so any row below the carbon row can have over an octet, and that's okay. So we're good. This would be the structure. You just rewrite it nicely so a TA understands what the heck you were doing. Okay? All right, so just do a couple Lewis structures at home or wherever you study to make sure you get used to it again. Let's talk a little bit about families. Oh, is there any questions about that example? Yes?
Well, we need to know resonance structures.
Well, yeah, nobody asked me about that, but resonance structures, technically yes, but we didn't recover it really until organic.
Okay.
So it's not a significant issue, but it's an issue that's out there.
Okay.
Yeah, it wasn't significant for some of the topics we've covered so far. It will be coming up.